There's a couple of preliminary things that we have to mention, some theoretical things before we get into it that'll just make life a little bit easier. So I'm going to start with center of mass of a multi-particle system of n particles. So the way I've typically shown it is there's an inertial frame, there's some point masses, because that's really all we're considering. Even if we do think of like a solid block, we're not considering any rotational dynamics or that it has any physical extent. We're just saying treat it like a particle. So if I have a collection of particles, there's going to be a center of mass, and I'll label that C, and you could define the location of that center of mass. So this gives the location, this vector gives the location of the center of mass, or COM, with respect to that n frame origin O. The way that the center of mass was defined, it was the mass weighted average of the location of all of the particles. So if you remember, RC is 1 over m, the total mass, sum from 1 to n of the locations of each of the particles, so capital R sub I, with the mass in front, mi. Now, it's sometimes convenient to think of a frame that's attached to the center of mass. So maybe I'll move this letter C out of the way and think of a frame attached to the center of mass. If we so desire, we could write the position of all of the particles, and I'll use little ri to represent the location of the particles, each particle with respect to the center of mass. So this would be from C to, this is mi, maybe I'll call it just C to I. Location of particle I with respect to the center of mass. And so you might think of it, it's, you know, with respect to a frame that's centered at the center of mass. With respect to COM centered frame. And I haven't yet given directions for those orange things, because that doesn't quite matter just yet. Now, the key thing here is if we were to write the location of the center of mass using these little r's, so location of the center of mass with respect to the center of mass, what are we going to get? We're going to get that it's the origin. It's 0. So 0 equals 1 over m. Sum goes from 1 to capital N, the number of particles, mᵢrᵢ. Since the center of mass is the origin, or the 0 vector of the, or I might just say a center of mass centered frame, any center of mass centered frame, so any orientation for those orange vectors. All right, so that's just saying instead of choosing some arbitrary origin O, if I actually knew where the center of mass was and then measured where's the center of mass with respect to here, oh, what do you know? It's at the origin. It's O. And so we can, this 1 over big M out in front doesn't mean anything. So we might just write this, sum of 1 from N, mᵢrᵢ equals 0. This is useful. This is important enough that I'll give it a name, even though the book doesn't. I'll call this the center of mass corollary. Hopefully I spelled corollary the right way. It just means if you measure where the center of mass is with respect to the center of mass, you get the 0 vector. You get the origin. So it's equivalent to, this is the origin of some frame centered at the center of mass. So that's useful. So yeah, for example, think of n equals 2. Then this sum is just m1 r1 plus m2 r2 equals 0, the 0 vector. So that means if you know the position of one of the particles, you could get the position of the other particle. So if we know the position of particle r2, and remember this will be in general, you know, moving around, so varying with time, then r1 is going to be negative m2 divided by m1 times r2. And let's just put function of time in there just so it's clear. So especially for just a 2-particle system, this kind of reduces the problem by 1, because all you really have to do is solve for the location of particle 2, and then for free, you get the location of particle 1. And you might be worried, I haven't even specified what coordinates. Yeah, right now it doesn't matter what those orange directions are or what frame I'm writing these with respect to. This is just it's a truth, especially useful in two particle systems, but maybe in even more. There's another thing. If you remember last time we talked about you could decompose the motion of this system of particles into the motion of the center of mass and then motion of them relative to the center of mass. So if I've got two particles, a blue and a black one, and there's their center of mass in between, and I don't know how that center of mass is moving, but then these two are just going to be moving around it. So there's motion of the center of mass and then motion relative to it. Those will come back later. So suppose the total external force, Fext, equals 0. So maybe the total external force cancels out, or there just aren't any external forces. Then that means that the motion of the center of mass is going to be with constant velocity. So it's going to be straight line motion. And then these things will swirl around it, the particles. Well, I don't know if they'll be swirling. They'll do things with respect to the center of mass. So at some later time, let's maybe call this t equals 0. At some later time, there's the center of mass, and these things are still just kind of moving relative to it. But in this case, the center of mass centered frame, I keep saying the as if there's one. We get to kind of pick those directions, right? Get to pick what those directions are. A center of mass centered frame is an inertial frame, meaning we could pick our frame. And why is that? Because it is moving with constant speed. So we could look at the dynamics with respect to the center of mass and do Newton's law in a center of mass centered frame. That's only true if the total external force is 0, because that means the center of mass, C, moves with constant velocity with respect to some other inertial frame. But it means you can jump onto the center of mass and view what the particles are doing with respect to the center of mass and write Newton's laws in it. So what about an n equals 2 situation? Here's a n equals 2. And suppose I've got two particles just connected by a spring. It's a linear spring. It doesn't bend. So it just makes sure that the particles are kind of moving back and forth. Well, get my particles. If I had a spring. If it was just these two particles and the spring connecting them, then they have a center of mass. Maybe one of these is much bigger than the other. I don't know. M1 and here's M2. So the center of mass is going to be closer to the bigger mass. But we could define an inertial frame centered on that center of mass and view the relative motion. Why is that? Because in this case, the only forces on the particles are internal forces, meaning forces due to another particle. The force on M2 is due to M1 through that spring that attaches them. So we could look at the motion of, let's call this is R2, and this is R1. And if this was viewed from some other frame, another inertial frame, we would see the center of mass, given initial conditions, the center of mass is generally going to be moving with respect to some frame, but it'll be moving on some straight line with constant speed. And so at a snapshot at some later moment, so let's call this again t equals 0, here's some later time. Maybe the springs have moved a little bit. I mean, the masses. So they've moved around. In fact, what do we expect for a spring? If I had a spring and let's say I had it spring loaded and I gave it a twist and then tossed it, and this is out in space, well, you can imagine this, the center of mass will move on a straight line, and then you'll just see some kind of weird pulsating motion of the spring as things go on. So this would be exactly like the situation up here in purple. We would have R1 is negative M2 over M1 R2. So it could just solve equations of motion from Newton's laws for R2. That is a function of time. Let's just do an example. I want to do this spring example. It's actually it's similar to one of the problems in the book. Not an example that it works through, but one of the problems. I think it's 213. So we'll go through this, and it's like a two-particle spring system. Sometimes I call it the dumbbell spring because it's just two particles and attached. And this is just, we'll do this only in 2D. So here's mass, one of the masses, and then some other mass. I'll say that they're equal masses. That'll make life a little bit easier. So M1 and M2 are both just equal to M. And the only force present is the spring force. So then from that, we can conclude something. This is an internal force. Right? It doesn't come from outside the system. It's the influence of each particle on the other. So there's no external force. So we can, that means that the motion of the center of mass will be not interesting. The interesting stuff is the relative motion. So we'll focus on the relative motion. We can focus on the relative motion. And two, we can use a center of mass centered frame as an inertial frame. Now, since these are equal masses, the center of mass will be right in the middle. And I will label, I guess, this N2 and this N1. That seems like a nice choice. It's kind of arbitrary. I could write the vector R2. I'll call this particle 2. So this is particle 2. This is particle 1. They don't really need the M's anymore. This is just 2. And this is 1. So here's R2. And here's R1. From the center of mass corollary, R1 equals negative, well, it's M over M. So this is just negative R2. So that's convenient. We probably don't want to write things in terms of these N1 and N2 directions. So now it's convenient to define a frame. And in this case, I would think a polar coordinate frame. So we will, I haven't labeled this is the center of mass, but it's the origin of our frame. I'll use some other color and define some direction. Here's ER, and here's E theta. So we'll focus on R2 and write its position in polar coordinates, which means not only the coordinates R and theta, but along with it, there's a polar coordinate frame, this green frame. So what happens here? R2 is r, whatever that distance is, times, or in the ER direction. What do we need to know about this spring? The spring, right? Springs are, the way springs work, they're parameterized by their spring constant, which is like newtons per meter, and then an equilibrium length. So we'll say that this spring has a stiffness K and an equilibrium length L naught. So if I were to sketch this out, for any kind of general distance between these two, maybe let's call that L, but there's an equilibrium length L naught. And it's probably better, instead of using L, to use something related to this R. So L is actually just 2 times R, right? This R in here is going to be it's a variable, it's a function of time. We'll write that the equilibrium length is 2 times R naught. R naught is just half of the equilibrium length, L naught. So this is a parameter that we'll use, but just end up being more convenient. So setting it up this way, where do we go from here? We can, at this point, write Newton's laws. We could do that. We know what the spring force is. But I don't want to. I'm pretty sure that we could, but I don't want to. I want to use an energy method and also angular momentum. So one of the things that we're going to be doing in this problem, so I say we could solve for motion using Newton's laws. And that would give us, we'll end up at the end of the day with theta double dot equals something, r double dot equals something. It's complicated, but we don't actually have to use Newton's laws. So instead, we'll use conservation of energy and conservation of angular momentum. Now, how would I know ahead of time that I should use these? I don't know if you've seen this in past classes, the idea of a central force problem. That means the force is only directed inward, which is a case that we have here. The force due to the spring, if we were to do a free body diagram, the force due to the spring, which is the only force present, we've got the force due to the spring on particle 2, the one we're focused on, and then it's kind of equal and opposite over here. So we have a central force, meaning the force is directed inward towards the center of mass, or the origin. Even if we didn't know that, it's possible that we could at least see. But in this case, it does work out that both angular momentum and energy are conserved. Energy is conserved because the only forces that are acting on this system come from conservative forces, meaning forces that come from a potential energy. Right? The only force present, or to be more technical, the only force that does any work. Because you might be asking, well, what's a force that doesn't do work? If I had a particle sliding on a table, there's the normal force of the table, and if it's frictionless, that normal force isn't doing any work. It doesn't do any work. You could calculate work, and nothing is being done by the normal force. So the only force present here is a spring force. Which is a conservative force. What does that mean? It comes from a potential energy. V, right? And so in general, V will be a function of the positions. What do we have for the spring force here? The potential energy, right, in a spring, it's 1/2 K, and then the stretch in the spring squared. And stretch could be positive or negative here. So this would be, remember we were saying, maybe I'll write this as L of t. L of t minus L naught squared. Remember, L is the instantaneous distance between the two. So that's the spring force. If we now write it in terms of R and R naught, so if you look up here in the upper left, we have, this is 1/2 K 2R minus R naught squared. Once you square that, you get 2K R minus R naught. And I've dropped that. It's understood that R is a function of time. That's the thing that will change. So this is the expression that I'll use for the energy in the spring. So to write the total energy, we also need to know what is the kinetic energy, the total kinetic energy. So this is the potential energy, or PE. What about the total kinetic energy? I'll write that as just capital T. It's the kinetic energy of particle 1 plus kinetic energy of particle 2. And you might guess, these kinetic energies are somehow going to be very similar to each other, maybe even identical. So what is T1? T1 is 1/2 m, and then the inertial velocity of particle 1. And by inertial velocity, that means velocity with respect to the center of mass. And then same for T2. It's 1/2 m R2. And these are squareds here. Due to the, what was that? The center of mass corollary up here. This implies if you take the inertial derivative, then it's the negative inertial derivative of the other. So if you square that, you lose the negative sign. I mean, not square, you take the magnitude and square it, you lose that negative sign. So these are actually the same. This is 1/2 m R2 magnitude squared. So it's equal to T2. So total kinetic energy is 2 times the kinetic energy of particle 2. Why am I focusing on particle 2? Just because it's easier to write. So let me write my center of mass, the inertial frame again, and my particle up here. This is particle 2. Here is R2. That's in the direction of the unit vector of this polar coordinate frame, ER, and then here is E theta. This is theta. And going from here to here is R. We hopefully have enough experience with polar coordinates now that we know what this will be. What is R2 dot? It is R dot in the ER direction plus R theta dot E theta. And if that bothers you, see example 1.2 of the book. So now take that, and you might be right. This is worrying for some people that we're taking the derivative with respect to time, with respect to the inertial frame, and yet not writing it in inertial components. But that's okay. It's just a vector. It's a vector. I mean, I don't know, pointing in this direction maybe. So I could write that vector in terms of N1 and N2 components, which I'd get something like that, or I could write it in terms of E theta and ER components. It's perfectly legit. Writing it this way, if I take the magnitude, so we get 1/2 m, take the magnitude of that, it's R dot squared plus R squared theta dot squared. The total kinetic energy is twice that. Looking up here, right, it's twice, it's 2. So that means total kinetic energy is m r dot squared plus r squared theta dot squared. Okay, cool. Now what? What about the total energy? Total energy is kinetic plus potential. So we've got enough to write that down. E equals m r dot squared plus r squared theta dot squared plus 2k r minus r naught squared. 3 of these things can vary with time. Is that right? Yeah, we've got r, all right, there's r dot could also vary with time, and theta dot can vary with time. The things that are parameters, maybe I'll do those in blue. There's m, k, and r naught. Those are just sort of given by the problem. This is the mass, maybe 1 kilogram. K is, I don't know, something in newtons per meter, and r naught is some length, an equilibrium length in meters. But these other things can change in time. However, since the only force present comes from the spring, total energy will be conserved. So this thing, this expression, so E is constant throughout the motion. This often bothers mechanical engineers because they're not used to looking at things in space. Like they're always having to deal with friction and details. Whereas when you're out in space, usually energy is conserved and you don't have to worry. It's great. And then in this contrived situation, right, there are not springs moving through space, as far as I know. It's an example problem. So E is constant throughout the motion because the only force present is a conservative force. So what does that mean? E at any time, so we might just write this out, r dot squared plus RT squared theta dot T squared plus 2k RT minus R naught squared is equal to whatever it was at the initial time, which means I'll call the initial time 0. Put a big 0 in there. R dot at 0 time plus R, the initial kind of half distance between the two, then the initial angular velocity squared plus 2k initial distance between these, the initial distance squared. So that's conservation of energy. What about, is there anything else that's conserved? Yes. Yeah, there is. Angular momentum. And why is angular momentum conserved? We talked about the special case that if the total external moment is 0, then if the total moment is 0, there's no change in the angular momentum. And the only forces present are these forces pointing inward, right? So we've got that, which means with respect to the center of mass, I guess I should keep drawing that weird symbol I can't draw so well. If we do R cross F, well, R and F are parallel, right? They're in the same direction, so you get 0, right? This is the force, and then this is the force on particle 2. So the total moment, say the moment on particle, I'm going to try to follow with the book uses L, as much as I don't like it. So R2 cross F2 is 0. L1 is R1 cross F1. Like this is F1. It's R1. Again, they're in the same direction. So because they're parallel, 0. Total moment, 0. So total angular momentum is conserved. But now we got to write what that angular momentum is. The total angular momentum, I'll just write it as h. And remember, angular momentum is, we're thinking of it as a vector now. It may only have one component. It'll be kind of the out of the screen component. But right now we're writing it as a vector. H equals the angular momentum of particle 1. I guess we could say particle 1 with respect to the center of mass, just so it's clear, right? There has to be a reference point, plus angular momentum of particle 2 with respect to the center of mass. So what are each of those? H1 with respect to C is, what was it? R cross momentum. So that's R cross M, right? Because this mass 1 is M and mass 2 is also just M. R2 dot and H2C is R2 cross M, R2 dot. Think up here, this should be a 1. But then remember, R1 equals negative R2, and R1 dot equals negative R2 dot. So the two negative signs cancel, and this is the same as H2C. So the total angular momentum with respect to the center of mass is 2H2C, which now we've got, we've written up above what R2 was. Let me repeat it here. R2 is R in the ER direction, and R2 dot was R dot ER plus R theta dot E theta. You take the cross product of those two, the only thing that's going to survive is M R squared theta dot in the ER cross E3 direction, which I didn't say what that was, but if we write ER E theta coming out of the screen to complete the right-handed coordinate system would be E3. So there's only that component. This is constant throughout the motion. Since there's only the E3 component, we should probably only look at that, E3. So M R squared, well, the way that I wrote it up above in terms of things changing in time. So that means at any time t, mass times radius squared times theta dot is going to equal whatever it was initially, M times R at the initial time squared theta dot at the initial time. And this is interesting. Well, I think I forgot it's a factor of 2. Sorry, that's bothersome. There we go. But the M's cancel out, right? 2 and the 2's. And we could rewrite this if we so wanted, writing it as theta dot at any time is equal to R over RT squared times theta dot at the initial time. So this is true. So this relates what the initial angular velocity is. Once I get this going, there's going to be a relationship between that and the initial radius and the current radius as this spins around. It's not going to be spinning around unless I chose some very careful initial conditions. These two masses, I give it initial condition, they're going to tend to oscillate kind of weird. It's going to look herky-jerky, unsteady rotation as it moves around. But here's what I'm going to do. I'm going to say, hey, I have a way of writing theta dot in terms of R and a couple of initial conditions in purple. And I'm going to plug that in to my energy expression. Again, what did I have up here? This horrendous looking thing, but it's not that bad. Where does this show up? This is theta dot as a function of time at any old time. So it goes there. I could plug it in, and I can't see both. I'm just going to hope for the best. You can take this expression and plug into the energy conservation equation. May as well, right? And then what did we have? We had m r dot at any time squared plus, and now I've got to plug in. So this is r at any time squared. And now we had theta dot squared. So that means square this thing. R at the initial time, that's going to be to the 4th power over R at this current time to the 4th power theta dot at the initial time squared. I got to get my parentheses right here. That was that's there. And then what? Plus 2k r minus r naught. 2k r minus the kind of half equilibrium length squared equals, and it just equals that whatever it was initially. And now what is the only thing that changes with time? In some sense, I've eliminated, well, the expression never had theta. Theta doesn't even show up, only theta dot. So I've got R, 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 R dot. Those are the only things that change in time. That means I could rewrite this as R dot. Can we write? No, I can rewrite as an expression R dot T squared equals, and I'll just leave it as F R T, and initial conditions, and those parameters K and M and R naught. But this is sort of the main thing, because what is R dot? That's dr by dt. I've got that squared. Dr dt at any time is some function of R. Once I've got it in this form, I could do some manipulation. It's just it's a math problem now, and I can use separation of variables to turn this into something that I can integrate. It might be useful though at this point to so first of all, let me take the square root of both sides. All right, square root of both sides. You might say, well, this should be plus or minus if you're careful. Yeah. Okay, plus or minus square root of f of r. I'm just going to call this h of r. So h of r is, I'll just define this to be square root of whatever this function f of r is. And hopefully I'm not losing you. I want to do a little plot. This is the current, distance of particle 2 from the center of mass versus the time rate of change of that. What you will tend to see for some initial condition is that this forms a cycle. So there's an upper half to the cycle and then a lower half to the cycle. And they're complete mirror images of each other. So this is h of r. down here, this is minus HR. And how do we interpret this? There seems to be a minimum. Let's call this R min, and then a maximum, R max. So throughout the motion, as these particles are kind of wiggling around, they're going to be going between some minimum and maximum distance. And this R min is half of that, right? Because we're measuring from the center of mass somewhere in the middle. And then it goes to a maximum distance. That's just the radial motion. And you can get this. So you would, well, let me finish, and then we'll actually do this numerically for an example. What are we doing here? So the plus part is the upper half of the cycle. That's this side. It's the plus side. Plus, then I'll put a blue minus. That means it's plus HR. We say the first half of a cycle of radial motion, dr by dt equals just the positive HR. And I'm going to call this time over here where we're at R min, let's call that t equals 0. And then we kind of go through this cycle, and then we end up here. And that's actually half the period. So I'll call this t equals capital T over 2. And then there's the lower half of the cycle, but it's going to be completely symmetric. It's just, this is going to look, it's not exactly sinusoidal, but it will be periodic, going up and down. So this is t equals 0. It's also t equals capital T. But just think of the first half of the cycle. We can rearrange this. So now do, what do you call that? Separation of variables. You can do that. And we'll get dt equals dr over hr. Right, we get t, everything that depends on t, and then the part that depends on r. We can now integrate both sides. So if I integrate this from 0 to capital T over 2, this gets integrated from R min to R max. R min and R max are the zeros of h of r. It's probably easier if you think of it, it's also the zeros of f of r. Because f of r, it doesn't have that square root thing in it, and it's just, it looks prettier when you plot it. But there's numerical tools to find the zero of, you know, something like, for any function, if I've got a curve, let's say this is f of r, it'll find those zeros. Sometimes you have to give it an initial guess. So if you're familiar with MATLAB, there's something called F0. You can even just Google root finder. So zeros are also called roots. It's just where that function crosses 0. All right, when we do this integral, you evaluate the left-hand side. That's easy. This is just t over 2. And then this left-hand side, you'd have to do something numerical. Unless h of r is something nice that you can solve analytically, but it's usually not going to be. So this is going to be the area under a curve 1 over hr, which is not a terribly nice looking curve. Right, this is hr. This is kind of a sketch of what hr is. And notice it goes to 0 at r min and r max, which means 1 over hr goes to infinity. So if we plot what this gives, then let me sketch in r max and r min. This is r. We're looking at something that goes to infinity, and then it has some minimum and it goes back up to infinity. So it's that area, and it's a finite area, so you would actually get some number. So we're talking about this area. That's the area in yellow. So we could try this. Let's try it for some situation, just to make life easy. So try a numerical example. And then I'll show you that it actually is true by independently. I wrote MATLAB code that solves Newton's laws and then shows the motion. So let's try, just to make life easy, mass is 1 kilogram. We'll take the stiffness to be 0.5 newtons per meter. The equilibrium length, half the equilibrium length, meaning this thing I wrote as R naught, we'll take that to be 1 meter. I'm choosing nice round numbers. You might have, like, why is K equals 0.5? Because I have a 2 times K, so I just want 2 times K to be 1. I'm just trying to pick something. You could use something else if you want. So those are the parameters. What about initial conditions? We'll choose initial conditions. R at the initial time is 1 meter, and theta at the initial time is 0. The initial radial velocity is 0 meters per second, and the initial angular velocity, pick something easy, 1, and the units are radians per second. So I guess here, if you want, this is 0 radians. Everything's measured in radians for angles to do these calculations. Okay, so if we do this, the formula for R dot, if I suppress what the units are, I'll get R dot squared equals, what's that? I'll get a, let me go up here. Don't forget, we had something. Oh, yeah. I guess I'm kind of giving you a lot here. Once we've rewritten that, the expression for energy, where we substituted in for angular conservation of angular momentum, this will end up giving you R dot naught squared plus R squared theta dot initially squared minus 2k over m R at any time minus R naught, not R at the initial time, but R naught squared. And we got something else, minus R initially to the 4th divided by theta dot initially squared, no, times that, and then divided by R squared. You plug in these initial conditions over here, and we'll get, this is 0, this is 1. I'm going to suppress the units. Minus, what's 2k over m? I've conveniently chosen it, so it becomes 1 times R minus 1 squared minus 1 over R squared. Okay, so that's kind of, let me just rearrange it. It looks like that. And it doesn't matter if you call this R or you call it X for doing integrals and things. So this is what f of R becomes for this choice of initial conditions and parameters, mass, stiffness, and equilibrium length. So we could find this, we could kind of sketch what we think the zeros of that could be, but we may as well just sort of plot it. So now I'm going to switch over to using my screen. My desktop's pretty messy, so don't judge. Let's go to MATLAB. Well, so there's also things online. So I may as well just show you what the things online give. You can find roots. So I put in, instead of R, I used the variable X, but this is the same thing. There's a root finder thing on Wolfram Alpha. And so it told me the roots. Because one of them is X equals 1, and the other one is this expression. I don't know. And so here's like the plot of that function f of R. But there it is. So it's got two roots. Something around 1, so 1 meter, and then the other thing is around 1.8. And it's precisely this. If I write approximate form, I don't know if that tells me a number. It's something close to like 1.8. And I don't know why this is not smart enough to do that. So let's try MATLAB. And what do we have? CLC. I don't know if you can see let me hide everything except MATLAB. Hopefully you can still see my screen. All right, so I'm typing what? First, I'll define a variable. So this is X goes from 0.1 to 2 in increments of 0.001. So that's just giving me something that I'll be able to plot. I should define something here. F equals, there we go. If you want to define a function of something, so this is defining f as a function of x with this expression. So this is what I wrote before, but in terms of r. Now I'm just writing in terms of x. That defines a function in MATLAB that takes in things. So how would I plot this? If I plot x and then f of x, well, double x, and I'll plot that in blue. And I honestly don't like the default line widths of MATLAB. So if I do 10 or something, there we go. Whoa. So it's hard to see the zeros until you zoom in. Let me write grid. And I'll zoom in. Let me just focus on where it seems to be crossing 0. So there's a 0 here around 1 and a 0 around 1.8. If I say x min, or here's what you do. If you haven't used it, I think it's F0 is the term. It looks for, this thing just says in the variable x for f of x, find me, and you have to give it some initial guess of where you think the 0 is. So what if I don't know? I think it's near 1, but maybe it's 0.9. It says, no, it's actually 1. Okay, then I'll call that x min. What about the other one? I don't know where it is. It looks like it's near 1.8. It gives me the precise, at least to whatever I've got here. And I'll just write that. I know I could write answer, but I'm going to do this. Oops, I ruined it. That was supposed to be max. X max is 1.8393. You might think, why am I not plotting the square root or 1 over the square root? Because it gives problems when you take the square root of negative numbers. So outside of this band, maybe it'll complain and say it's got complex numbers. In fact, let's just try it. In fact, that range for x is too big. Let me do 1.9. And over here, just 0.9 to 1.9. Plot. Maybe I'll do this in like red. Square root. Yeah, there we go. And that pretty much matches what I thought for at least the upper half, right? This is it's a way to make everything font big. Ooh, yeah, there we go. This is R along this horizontal axis, and then R dot or dr dt. So this is showing that thing, and there'll be a lower half. But if we integrate, does this work? Yeah, integral with the variable x, 1 over square root of f of x. If you remember, h is defined as f of x. And we're going from x min to x max. Maybe this will give us something. Yeah, it gives us something with a complex component. So you have to be careful. I'll just add something tiny and then subtract something tiny, so it's not getting into that problem zone. Okay, that's cool. remember that was the half period, that the answer to that integral. So that's our period, around 4.5. So that's the period in seconds for the motion in the radial direction. That's what we would get. If you want to see what the actual motion looks like, the details of this aren't important right now, but I was able to write the Newton's laws and then the second order ODEs. You turn them into first order ODEs. I'll probably go through this more carefully at some other point. I've put in the parameters that I just wrote, and then initial conditions. There's 4, right? Initial R dot, initial theta dot. I'll have this go from 0 to 30 seconds with outputting every 0.1 seconds. And then there's ODE 45. It's dumbbell spring ODEs. Just run this. Cool. Now I'll open another figure. Yeah, I meant that. Figure. Let's plot the R as a function of time so you can see that. I think I do call it R. So T versus R. I like blue, and I like line width that you can see. There we go. And there is a plot. I'm not writing what this x-axis is, but that's time, and this is radius. So you could see it's periodic. With a period of what? It would be from peak to peak or trough to trough. This seems to start down here and then end at another trough. So if I zoom in, it should be around 4.5 something. Yeah, cool. It is. And you might be wondering, well, what about theta? Theta just keeps on increasing. So that means this thing is turning around. It might be easier to see if we plot it as, I don't know if you know the term mod. Every time this thing exceeds 2 pi, it just goes back to the beginning. So it's, and then it goes back. Notice the period here, a period here would be going from 0 to 2 pi, and this is not the same period. It's not near 4.5, it's something else. So the period of the radial motion and the period of the theta motion are not necessarily the same. Now the real excitement comes in, trying to visualize what this motion is. So I've written a program that does that. It's called animation. Not that, animation. So hopefully this works. There we go. So it's plotting. The black particle is particle 2. And we're also plotting particle 1 in blue, but we're also plotting the track of particle 2. So you could see how it's moving around. And this is kind of what we expected. If you give a spring any kind of general push and turn, there'll be this oscillatory motion as they expand and contract, but then it's also turning around. And you notice it's not closing back up on itself. And it won't necessarily, but it's kind of cool to see. You could change the initial conditions and see different things. I've already done that. Here's starting with a kind of compressed spring and releasing, and you can see what happens. This is just from a screen recording, but it shows it, and you go, whoa, it's doing something weird, but definitely more spring-like. And so this follows that rule that you expect from watching, ice skaters. When the ice skaters, they get some angular momentum and then they bring their arms in, things turn faster. This is turning the fastest when the two masses are close together. But here it's not due to bringing arms in, it's due to the masses coming together due to just the spring. So I can show that again. That's kind of neat. All right. So that's all I wanted to show today. Okay. Thanks for hanging in there.